So in this video, we are going to learn about how the Raft algorithm actually works. Okay, so cool. So this video will be part of, I will divide it into two parts. Okay, in the first part, we will see like basically how Raft maintains the leader election process inside itself. And then in the second part, and both part will be in the same video, we will see like how Raft basically uh, maintain the consistency, strong consistency of the data. Okay, so we cannot say it's 100% strong consistency, but let's see, then we can understand. Okay, so first part is like how do Raft maintains Raft elects the leader. Okay, so let's say this is the primary database. Okay, these are the secondary database. Okay, on which the data are going to be replicated. Okay, now what happens that this primary actually sends a heartbeat to each of the secondary databases. Okay, so let's say this primary was created at 1 p.m. Okay, 1 a.m. Okay, the secondary was created at 1:01 a.m. Okay, and the third one is created at, let's say, 1:05 a.m. Okay, so every 10 minutes, Raft leader will send a heartbeat to each of the secondary nodes. Okay, each of the secondary nodes. Cool. And every time it sends the heartbeat and gets the acknowledgement, it increases a epoch. Okay, so what is basically epoch? Epoch is an integer. Okay, which will increase as soon as any update comes up. Okay, so let's say uh, at time t1. Okay, at time t1, the epochs are like something like this. The primary has the epoch of 21. Okay, so previous to that there was epoch of 20. Previous to that there was epoch of 19. I'm just keeping all these three. Why? So that I can explain it better. Okay, at time t1, this guy also have epoch of 21, 20, 19. Okay, and similarly this guy also have epoch of 20 and 19. This yet doesn't have the epoch of 21. Okay, now what happens that a new it have to send a new heartbeat to each of them. Okay, so the new epoch is 22. Okay, so this also increased by 22. Okay, but let's say due to some reason what happened, the router over here stopped working. Okay, the router over here stopped working. So now this guy will say, hey buddy, I should have received a epoch, like I should have received a heartbeat, but I have not received any. So what's the matter? So is the primary down, or I have a shitty network? It will go and ask this guy that is the leader down or what happened. This guy will say, no, actually the leader is not down. Most probably you have a route problem. Okay, and wait for some time and then retry for the heartbeat. Cool. Once it gets the heartbeat, okay, then it will update its epoch from 21 and then 22. Cool. Now, what if the leader goes down? Okay, what if the leader goes down? So let me just make the video picture once more. Okay, so this is the leader. Okay, this is the leader. These are the followers. Okay, these are the followers. Now, what happened is that uh, it was having a epoch of 21, 20, 19. Okay, and there is one more follower, let's say. Okay, so this was having a epoch of 20 and 19, and this was having a epoch of 21, 20, 19. Okay, this went down. Okay, now this any one of them, let's say this guy noticed that I have not received the heartbeat, so it asked for a leader election. Okay, now as we have seen in the previous lectures, like anyone cannot become randomly a leader. So now, as we know that this guy is outdated, if he becomes the leader, he becomes the next leader, then there will be a split brain problem. The 21th number of epoch will get completely lost. So if there was a data, okay, which like updated or new entry which came between the epoch 20 and 21, it will get completely lost, right? So due to, so that this problem doesn't happens, the follower will do a leader election. So let's say there is one more follower. Okay, there is one more follower. This guy has let's say 21, 20, and 19. Okay, this guy also have this. So what it does, it sends an RPC to everyone, okay, saying that can I become the leader? Okay, can I become the leader? So this guy says that, hey, no, you have epoch. And how does he sends the RPC? He says that I want to be a leader because I have not received RPC, like heartbeat RPC from leader, and my current epoch is 20. Okay. So this guy says that, hey, that's fine. If you didn't receive any heartbeat, can you wait for some time? This guy waited for some time and he didn't receive the heartbeat yet. Okay. So he says, then I want to be the leader. Now, this guy says, okay, you want to be a leader, but your data is not up to date. You only have epoch till 20. I have epoch till 21. So you are not the correct person to be the leader. Okay. So it denies it. It says you cannot be the leader. Okay. I will be the leader. So this is case number one. Okay. Case number two is, let's say any of the follower who has the highest amount of the epoch started the leader election. Okay, so he says, hey, I want to be a leader. Okay, do you elect me to be a leader? Okay, so he says, okay, you can be the leader. I don't have the latest epochs. So what is the latest epoch? He says 21 is the latest epoch. So he sent this 21 in this RPC only. So he updates himself with 21 and says, okay, you can be the leader. Okay, so this is case two. So in first case, what we have seen, that someone who has less epoch, okay, less epoch, sends the RPC and he got denied because someone else have a more updated epoch. In the second case, what we have seen, that someone with greater epoch, like someone with the more updated epoch, sends the request to some other follower who has lesser epoch. So in that case, the person or the DB having the lesser epoch will update himself with the recent epoch. Okay. Now case number three. Case number three is, let's say there are two databases. Okay. This is also having epoch of 20, 120, and 19. This guy is also having epoch of 21, 20, 19. Okay. So this guy will send, I want to be a leader. Okay. And this guy will say, okay, cool. You can be the leader because uh, what I can see from my side, you have the latest epoch. Okay. So now finally, this guy becomes the leader. Okay, so in this case we have to make sure that the leader who was previously the leader. Okay, so let's say this were the followers. Okay, this were the followers. Okay, and the leader goes down. Okay, and let's say he send a proposal for becoming a leader. Okay, he sends a proposal to becoming a leader, and once he becomes the leader, this guy, whenever it comes up, let's say after 1 hour it came up, he cannot become the new leader. He have to replicate everything from the new leader. Okay, now this guy is the leader, and this guy, the previous leader, have to replicate everything from the old leader. I'm sorry, from the new leader. Okay, so this is how the leader election actually happens in Raft. So that was part number one, where we have decided who will become the leader who will become the leader if the current leader goes down. Okay. Now part number two, how will a client write a data to maintain the maximum like consistency? Okay. So let's say this is the leader. Okay. These are the followers where the replication will happen. Okay, these are the followers where the replication will happen. Okay, so whenever a client writes a data, okay, whenever a client writes a data, okay, the leader will only wait until, so obviously, like we know, there are two ways: either like synchronously we replicate to every places and then say the client that hey, it's done, but that is extremely slow. Okay, or what we can do, we can asynchronously send data to everyone. Okay, once the leader has done the write, okay, it will say the client that it's done, and then asynchronously it does the replication. But the problem with this, that is, what if the leader goes down, then the whole data is lost, right? The recent data is lost, so it's not reliable. So what Raft does, okay, what Raft does, it it writes the data to majority of the nodes. Okay, majority of the nodes. Okay, so for example, if there were like let's draw one more replica. So now if there are like total of 5 nodes, what it will do, it will always uh, like 2n plus 1 by 2. So like there are 5 nodes, so if there are 3 nodes which have written the data, then it will send the client that okay, it's done. Then in background asynchronously it can replicate to other nodes also, doesn't matter. Okay, so if the majority of the nodes, okay, majority of the node have done the write, then it will send the client that the write is done. Now, how will it manage? See, like how will it manage that all the writes are done? Okay, let's see step by step. Okay, so let's say this guy, the primary, okay, primary was having A, B, C, D data. Okay, so previously what it was having A, B, C, and then a client comes and it writes the data D. Okay, so A, B, and C it is there. So in data also we will put some version kind of integer. Okay, so A was, let's say, 1, B was 2, C is 3, and D will become 4. Okay, so as soon as the client writes D, it doesn't get the response. Okay, it is not yet committed. Now these are the followers. Okay, these are the followers. Let's say this guy also have replicated A, B, C previously, and this guy has only replicated A and B. So how Raft will basically send the information to this 2DB. So like we have seen in previous lectures, in vector versioning, it have to send whole data. But obviously, like if the database is huge, sending the whole database is stupid. Okay, it will take the whole network bandwidth. So what it will do, it will send that I want to write D, okay, whose version is 4, and D is written on top of C, whose version was 3. Same here also, it will say I will write D whose version is 4, and I want to write D on top of C whose version was 3. Okay, once it sends the data to this follower checks, do I have C whose version is 3? Yes, I do have. So now what I can do, I can write D whose version is 4. It says, okay, you can do it. Okay, but this guy who doesn't have C, so he says that he master wants to write D, which is whose version is 4 on top of C. Do I have C? It says that, oh no, shit, I don't have C. Okay, so this was 1, this has 2. So what it sends to the primary, that hey buddy, I don't have C. Okay, now it says that okay, if you don't have C, can you write C, can you write C whose version is 3 on top of B whose version is 2? Then this follower checks, can I write C on top of B whose version is 2? Yes, I can do that. So it writes C and it says okay, done. Then again it sends a D whose version is 4 on top of C whose version is 3. Now it checks, can I write this? Okay, I can write this. Now this follower is also updated. Okay, once both of them are okay, once both of them are done, then it will send the client that yes, the write has been completed, it's committed, thank you. Okay, then asynchronously in other replicas also the same thing will happen. Okay, but for that the client doesn't have to wait. Okay, asynchronously in other client also the replication will happen. Okay, so from this video, what we have seen that Raft is maintaining a single leader replication. Okay, and it completely use the distributed distributed consensus distributed consensus. Okay, I got tongue twists. Okay, it is following the distributed consensus. Okay, for we have seen the flow in which how Raft actually maintains a leader. Okay, even in case of failover, it uses a heartbeat, and it how it prevents split brain. And the second thing is whenever a data is being written, how does it maintains strong consistency? Okay, so it basically writes the data to the majority of the nodes. Okay, once the majority of the nodes have written the data, it sends the client that okay, I am done, and then it replicates the data asynchronously to other applications. Cool. What are the pros and cons of Raft algorithm? In the leader election part as such, there is no con, only uh, but in the right path. Okay, the first con which you have seen, like this flow, like it had to do 4 rpcs, right? Actually 2 rpcs, this will be one, this will be the second one. Okay, so it is slow. You are not completely removing the two-phase commit. It has to do a two-phase commit to the majority of the nodes, although two-phase commit only we say when it is doing to all the nodes. But actually if you see like in top view, it is doing to the majority of the nodes. So we can say it is not 100% removing the two-phase commit, and as we know two-phase commit is slow. This is the first problem. Okay, and the second problem is there any second problem? Yeah, I don't see any second problem. Yeah, but the good part is like data is consistent. Data is not going to lose. Okay, A- and yeah, one thing I forgot to say is that in the data path, okay, obviously before committing the message, what it can do, it can maintain a write ahead log. Okay, it can maintain a write ahead log. Why does it maintain a write ahead log? Like using this write ahead log actually. Okay, if for like what I have said, if the primary actually goes down for a split amount of second, okay, or something like something bad happen, it can actually replicate everything from the write ahead log. Okay, if there is no other leader who has been elected. But if there is other leader who has been elected, then okay, it cannot become a primary anyway. Okay, uh, I am not very sure about this write ahead log, but this was just an addition which I have done on top of Raft algorithm. Right, Raft algorithm only contains the part where it does the leader election and the right like data path. Okay, cool. Thank you, and hope so you will like this video.